What if I told you that the secret to our future might lie in the distant past of our solar system? Imagine diving into a world where ancient Mars had lakes and rivers, or where Venus might not have been the hostile planet we know today. In this video, we're going to uncover the mysteries of what the planets were like 3 billion years ago. By understanding these ancient conditions, we can unlock the secrets that could revolutionize how we see our place in the universe and even our own planet's future. Curious about how the rocky terrains and atmospheric wonders of these planets looked billions of years ago? Stay with us till the end as we explore the hidden past of our neighboring worlds. The first thing we need to understand is Earth's early atmosphere. Around 3 billion years ago, Earth's atmosphere was vastly different from what we breathe today. It was primarily composed of methane, ammonia, water vapor, and hydrogen. Oxygen, which is crucial for most life forms today, was nearly absent. This primordial soup created an environment ripe for the formation of simple organic molecules, setting the stage for early microbial life. Picture a world enveloped in a thick, hazy atmosphere with volcanic activity releasing gases into the air. These volatile conditions contributed to the creation of primordial oceans, rich with the chemical building blocks of life. In these oceans, the first simple life forms began to emerge, possibly around hydrothermal vents where volcanic activity provided the necessary heat and nutrients. These early microbes, known as anaerobic bacteria, thrived without oxygen. They could harness energy from chemicals like hydrogen sulfide, which was abundant in this early environment. This period was crucial for the development of early life, paving the way for more complex organisms that would eventually populate Earth. Understanding Earth's early atmosphere and its role in supporting microbial life helps us appreciate how life can begin in the most extreme and unlikely conditions. This knowledge not only informs us about our own origins, but also guides our search for life on other planets where similar conditions might exist. So as we delve deeper into the mysteries of our solar system's past, remember that the secrets of ancient atmospheres hold the key to unlocking the potential for life beyond Earth. The first thing we need to understand is Earth's early atmosphere. Around 3 billion years ago, Earth's atmosphere was vastly different from what we breathe today. It was primarily composed of methane, ammonia, water vapor, and hydrogen. Oxygen, which is crucial for most life forms today, was nearly absent. This primordial soup created an environment ripe for the formation of simple organic molecules, setting the stage for early microbial life. Picture a world enveloped in a thick, hazy atmosphere with volcanic activity releasing gases into the air. These volatile conditions contributed to the creation of primordial oceans, rich with the chemical building blocks of life. In these oceans, the first simple life forms began to emerge, possibly around hydrothermal vents where volcanic activity provided the necessary heat and nutrients. These early microbes, known as anaerobic bacteria, thrived without oxygen. They could harness energy from chemicals like hydrogen sulfide, which was abundant in this early environment. This period was crucial for the development of early life, paving the way for more complex organisms that would eventually populate Earth. Understanding Earth's early atmosphere and its role in supporting microbial life helps us appreciate how life can begin in the most extreme and unlikely conditions. This knowledge not only informs us about our own origins, but also guides our search for life on other planets where similar conditions might exist. So as we delve deeper into the mysteries of our solar system's past, remember that the secrets of ancient atmospheres hold the key to unlocking the potential for life beyond Earth. The early Earth's landscape was equally fascinating and tumultuous. Around 3 billion years ago, the planet's surface was dominated by intense volcanic activity. Imagine towering volcanoes spewing molten rock and gases into the air, shaping the rugged terrain. Lava flows created vast basalt plains, while volcanic islands dotted the primordial oceans. These oceans were not like our modern seas. They were rich with minerals and bubbling with geothermal activity. The presence of water was crucial as it acted as a solvent and medium for chemical reactions that led to the origin of life. Beyond the volcanic landscapes and oceans, Earth's surface also started to show signs of continental formations. Although the continents as we know them did not yet exist, proto-continental crusts were beginning to form. These early landmasses were small and unstable, constantly being reshaped by tectonic forces. Plate tectonics played a vital role in this period, as the movement of Earth's crustal plates caused the formation and destruction of early continental formations. This dynamic process not only sculpted the planet's surface, but also influenced the distribution of minerals and nutrients essential for life. The interplay between volcanic activity, the presence of water, and the early formation of continents created a unique and ever-changing landscape. As we explore these early landscapes, we gain insights into how Earth's surface conditions contributed to the emergence of life and how similar processes might unfold on other planets. Understanding this ancient world helps us appreciate the delicate balance of factors that make a planet habitable and guides our search for life beyond Earth. Ancient Mars was a planet teeming with geological activity and, intriguingly, signs of water. Imagine a world where vast networks of rivers carved channels into the Martian surface and lakes dotted the landscape, much like the ones we see on Earth today. Around 3 billion years ago, Mars had a much thicker atmosphere, which allowed liquid water to exist on its surface. This ancient atmosphere was likely rich in carbon dioxide, creating a greenhouse effect that kept the planet warm enough to support water in its liquid form. Evidence of the Martian water cycle comes from numerous valley networks, outflow channels, and sedimentary deposits observed by rovers and orbiters. These features suggest that not only did water flow on Mars, but it did so in significant amounts, potentially creating an environment where life could have existed. The presence of clay minerals, which form in the presence of water, further supports the idea that Mars had long-standing bodies of water. Microbial life, if it existed, might have thrived in these ancient Martian lakes and rivers. The discovery of recurring slope lineae, dark streaks that appear and grow during the warmer months, indicates that liquid water might still flow on Mars today, albeit in much smaller quantities. This tantalizing evidence fuels our quest to find signs of past or present life on the red planet. Understanding what early Mars was like provides invaluable insights into the planet's potential to support life. The presence of water, combined with the right chemical conditions, could have created habitable environments similar to those on early Earth. As we continue to explore Mars, we hope to uncover more clues about its watery past and the possibility that life once flourished on this now barren world. If ancient Mars could support water and possibly life, it raises exciting possibilities for other planets and moons in our solar system, guiding our search for extraterrestrial life. Mars' ancient atmosphere played a crucial role in shaping its landscape and potentially supporting life. Around 3 billion years ago, Mars had a much thicker atmosphere than it does today. This ancient Martian atmosphere was rich in carbon dioxide, which is key to creating a greenhouse effect. The greenhouse effect, in turn, kept the planet warm enough to support liquid water on its surface. Scientists believe that this thicker atmosphere helped trap heat, preventing it from escaping into space and allowing for stable, warmer conditions. Imagine a planet where the sky is tinged with a reddish hue due to the abundant dust particles suspended in the air. Mars' thick atmosphere would have been much more dynamic than the thin, arid one we see today. This dense atmosphere could have sustained a more vigorous water cycle with clouds, rain, and perhaps even snow falling on the Martian surface. The presence of liquid water is evidenced by the numerous valley networks and outflow channels that crisscross the planet. These features suggest that rivers and lakes were once common, carving out canyons and depositing sediments much like the processes seen on Earth. Furthermore, the atmosphere likely played a role in the formation of various minerals that are indicative of water. For instance, clay minerals found on Mars require the presence of water to form, and these have been detected in multiple locations on the planet. The existence of these minerals points to long-standing bodies of water that could have lasted for millions of years. The dense carbon dioxide atmosphere also set the stage for potential microbial life. Early Martian life, if it existed, might have been similar to the anaerobic bacteria found on early Earth, thriving in environments rich in carbon dioxide and hydrogen. These microbes could have utilized chemical energy sources to survive in the ancient Martian lakes and rivers. As the atmosphere gradually thinned over time, due to various factors such as solar wind stripping away the atmospheric particles, the water on the surface began to evaporate or freeze, leading to the dry and cold Mars we see today. However, understanding Mars' thicker, ancient atmosphere helps us appreciate the dynamic changes the planet has undergone and how it might have once been more hospitable to life. This knowledge not only sheds light on Mars' past, but also informs our search for life on other planets and moons in our solar system. By studying the ancient atmospheres of planets like Mars, we can better understand the conditions necessary for supporting life and refine our techniques in the quest to find extraterrestrial habitats. The next planet on our journey through time is Venus. Imagine Venus 3 billion years ago, a planet that might have been strikingly different from the scorching, inhospitable world we see today. Back then, Venus could have had a much cooler and more temperate climate. Scientists believe that in its distant past, Venus might have had vast oceans of liquid water and a more Earth-like atmosphere. The thick, toxic clouds of sulfuric acid that veil the planet now were likely absent, allowing the planet to retain heat from the sun without creating the extreme greenhouse conditions we associate with Venus today. This ancient atmosphere might have been rich in carbon dioxide, similar to early Mars, but also contained water vapor and possibly even nitrogen. These components could have created a balanced greenhouse effect, maintaining a climate that could support liquid water on the surface. The presence of water is crucial as it is a key ingredient for life as we know it. The idea that Venus could have been habitable is supported by computer models simulating ancient climates. These models suggest that with the right conditions, Venus could have sustained stable, warm temperatures and liquid water for hundreds of millions of years. If life did exist on early Venus, it might have been microbial, thriving in the shallow seas and utilizing the abundant sunlight for energy. However, this potentially habitable period did not last. Venus experienced a drastic change due to a runaway greenhouse effect. Volcanic activity released massive amounts of carbon dioxide into the atmosphere, increasing the greenhouse effect to extreme levels. This caused surface temperatures to skyrocket, boiling away any existing oceans and leaving the planet a searing, dry desert. The loss of water further accelerated the greenhouse effect, as water vapor is a potent greenhouse gas. Without liquid water to regulate the climate, Venus transformed into the hottest planet in our solar system, with surface temperatures hot enough to melt lead. Understanding Venus's transformation from a potentially habitable world to its current state helps us appreciate the delicate balance required for a planet to remain hospitable. It also serves as a cautionary tale about the impacts of greenhouse gases on planetary climates. By studying Venus's past, we gain insights into the possible fates of Earth-like worlds and the importance of maintaining climate stability. As we uncover these ancient secrets, we hope to apply this knowledge to our search for life beyond our solar system, focusing on exoplanets that might be in the habitable zone of their stars. The climate of ancient Venus was likely far more temperate than the harsh, scorching conditions we associate with the planet today. Imagine a world where gentle breezes carried clouds across a sky that might have looked remarkably similar to ours. Around 3 billion years ago, Venus could have had a climate capable of supporting vast oceans and a more Earth-like atmosphere. During this period, the planet likely had a balanced greenhouse effect, allowing it to retain just enough heat from the sun to maintain liquid water on its surface. This ancient atmosphere was probably rich in carbon dioxide, water vapor, and possibly even nitrogen, creating conditions suitable for a temperate climate. Unlike the thick, toxic clouds of sulfuric acid that shroud Venus now, the ancient sky might have been clearer, with clouds that contributed to a more stable and hospitable environment. Computer models simulating Venus's past climate suggest that the planet might have enjoyed these stable, warm temperatures and liquid water for hundreds of millions of years. This habitable period could have allowed for the development of microbial life, perhaps flourishing in shallow seas and harnessing sunlight for energy. The balance of atmospheric gases played a crucial role in maintaining these conditions, with water vapor acting as a significant greenhouse gas that regulated the planet's temperature, preventing extremes. However, this delicate balance was eventually disrupted. Massive volcanic activity on Venus released enormous amounts of carbon dioxide into the atmosphere, tipping the scales towards a runaway greenhouse effect. As the greenhouse effect intensified, surface temperatures soared, boiling away any existing oceans. The loss of water further exacerbated the situation, since water vapor is also a potent greenhouse gas. Without liquid water to moderate the climate, Venus transformed into the hostile environment we see today, with surface temperatures hot enough to melt lead. The study of Venus's ancient climate not only provides a window into the planet's past, but also serves as a powerful reminder of the impacts of greenhouse gases on planetary climates. By understanding how Venus transitioned from a potentially habitable world to its current state, we can gain valuable insights into the factors that contribute to climate stability. This knowledge is essential as we search for Earth-like planets beyond our solar system, helping us identify worlds that could sustain life. The story of Venus underscores the importance of maintaining a delicate balance of atmospheric conditions to preserve habitability. As we continue our exploration, we hope to find exoplanets that have managed to maintain this balance, offering new possibilities for discovering extraterrestrial life. Analyzing the Moon's surface and its interaction with Earth 3 billion years ago, we uncover a story of intense geological activity and a closer, more dynamic relationship with our planet. The Moon's surface during this period was marked by significant volcanic activity. Imagine vast plains of basaltic lava flows creating the dark maria or seas that still characterize the lunar surface today. These volcanic eruptions were driven by the Moon's internal heat, which was much higher than it is now. This heat, primarily from radioactive decay and residual formation energy, caused molten rock to seep through the cracks in the lunar crust, forming extensive basaltic plains. The Moon's interaction with Earth was also quite different. The Moon was much closer to our planet, appearing significantly larger in the sky. This proximity resulted in stronger gravitational interactions, influencing both the Earth's and the Moon's geologies. The gravitational pull of the Moon caused substantial tidal forces on Earth, leading to higher tides and more pronounced tidal heating. This tidal heating could have contributed to volcanic activity and the movement of tectonic plates on early Earth, further shaping its landscape. The closer distance between the Earth and the Moon also meant that the Moon's gravitational influence on Earth was stronger, impacting the length of the day and the stability of Earth's axial tilt. These gravitational interactions played a crucial role in developing Earth's environmental conditions, potentially influencing the climate and the evolution of life. The volcanic activity on the Moon around 3 billion years ago left a lasting imprint on its surface. The smooth, dark maria that we see today are remnants of these ancient lava flows. These volcanic plains cover about 16% of the lunar surface, primarily on the near side of the Moon, which constantly faces Earth. This distribution suggests that the gravitational forces exerted by Earth may have influenced the location and extent of volcanic activity on the Moon. Studying these ancient volcanic features provides crucial insights into the Moon's geological history and its thermal evolution. It also helps us understand the Moon's role in shaping the conditions on Earth. The intense volcanic activity on the Moon during this period contributed to the release of gases, which may have created a transient, thin lunar atmosphere. Although this atmosphere was short-lived, it highlights the dynamic processes that were occurring on the Moon's surface. The interaction between the Earth and the Moon 3 billion years ago was a complex and dynamic dance, with each body influencing the other's geological and environmental conditions. By analyzing the Moon's surface and its volcanic history, we gain a deeper understanding of the interconnectedness of our solar system and the factors that have shaped our planet's development. As we continue to explore the ancient past of our neighboring worlds, we uncover the profound ways in which these celestial bodies have influenced each other, offering vital clues about the evolution of our solar system and the potential for life on other planets. The next part of our journey takes us to Mercury. Imagine Mercury 3 billion years ago as a planet of stark contrasts and intense geological activity. Mercury's surface during this period was dominated by heavy volcanic activity and an environment shaped by frequent meteor impacts. Picture a world where molten lava flows filled vast plains, creating smooth areas known as intercrater plains. These plains were formed as lava oozed through cracks in the crust, cooled and solidified, smoothing out older, heavily cratered landscapes. This volcanic activity was driven by Mercury's internal heat, which was much higher during its early history. Due to its proximity to the Sun, Mercury experienced extreme temperature fluctuations with scorching days and freezing nights. However, 3 billion years ago, its surface and internal dynamics were more active than they are today. Frequent meteor impacts caused by the planet's close position to the Sun and sparse atmosphere led to a heavily cratered terrain. These impacts not only shaped the surface but also contributed to the planet's geology by causing shock melting and creating new geological features like impact basins. One of Mercury's most distinctive features, the Caloris Basin, is an enormous impact crater that likely formed around this time. This basin, and others like it, was a result of massive collisions with asteroids or comets, which released significant amounts of energy and caused widespread geological upheaval. The impact that created the Caloris Basin was so powerful that it caused seismic waves to travel through the planet, creating a jumbled terrain known as weird terrain on the opposite side of Mercury. Mercury's thin exosphere, composed mainly of oxygen, sodium, hydrogen, helium, and potassium, was constantly replenished by volcanic outgassing, sputtering from solar wind, and the impact of micrometeoroids. This exosphere was too thin to exert any significant pressure, but it was indicative of Mercury's active geological and atmospheric processes. Understanding Mercury's ancient geological activity helps us piece together the planet's history and its evolution over billions of years. By examining the volcanic plains, impact craters, and basins, we gain insights into the dynamic processes that shaped Mercury's surface. These studies also provide a window into the early solar system, where planetary bodies frequently collided and reshaped each other's landscapes, offering valuable clues about the forces that have influenced not only Mercury, but also the other planets in our solar system. Jupiter's formation set the stage for many of the dynamic processes within our early solar system. Around 3 billion years ago, Jupiter had already formed from the Primordial solar nebula, a giant cloud of gas and dust left over from the Sun's formation. The process began with the coalescence of small particles into larger planetesimals, which then merged to form a solid core. This core rapidly attracted surrounding gas, primarily hydrogen and helium, due to its strong gravitational pull. Jupiter's immense size and mass influenced the orbits and formation of other celestial bodies within the solar system. As the largest planet, its gravitational field was powerful enough to affect the trajectories of nearby asteroids and comets. This gravitational dominance also played a crucial role in shaping the asteroid belt located between Mars and Jupiter. By preventing these rocky bodies from coalescing into another planet, Jupiter essentially carved out this region. Jupiter's early formation also contributed to the delivery of water and organic molecules to the inner planets, including Earth. As the gas giant moved through the solar system, it acted as a gravitational slingshot, redirecting comets and icy bodies inward. These impacts delivered vital materials which played a significant role in the development of Earth's oceans and possibly even the emergence of life. Additionally, Jupiter's presence helped stabilize the orbits of the inner planets by preventing excessive inward migration of primordial planetary bodies. Analyzing the gas giant's early formation helps us understand the delicate balance and interplay of gravitational forces that shaped our solar system. Jupiter's fast accumulation of mass and its resulting gravitational influence prevented the formation of other large planets in the asteroid belt and protected the inner solar system from excessive bombardment by stray planetesimals. Moreover, Jupiter's strong magnetic field, generated by its rapid rotation and internal metallic hydrogen, has been shielding the inner planets from intense solar wind and cosmic radiation for billions of years. This magnetic field traps high-energy particles, creating a magnetosphere that extends far beyond the planet itself. Understanding Jupiter's formation and early influence on the solar system provides valuable insights into the dynamic processes that govern planetary systems. Jupiter's gravitational dominance, early migration, and magnetic protection have all contributed significantly to the development and stability of our own planet and the broader solar system. By studying these early events, we can better appreciate the complex factors that make our solar system unique and apply this knowledge to the study of exoplanets and the search for life beyond our cosmic neighborhood. The early conditions on Jupiter's moons, particularly Europa and Ganymede, were vastly different from what we observe today. Around 3 billion years ago, these moons were already influenced by Jupiter's immense gravitational pull, shaping their geological and potentially hydrological features. Europa, known today for its icy surface and subsurface ocean, likely had a warmer core due to tidal heating. This process, driven by the intense gravitational interactions with Jupiter and neighboring moons, caused internal friction that generated heat. Imagine a world where the ice crust was thinner and more dynamic, allowing for frequent resurfacing events. This would create a young, relatively smooth surface, constantly renewed by cryovolcanic activity. Beneath this ice layer, a salty, liquid ocean might have existed, kept warm by the heat from the moon's core. This environment could have been conducive to the development of microbial life, especially around hydrothermal vents on the ocean floor, similar to early Earth conditions. Ganymede, the largest moon in the solar system, also experienced significant tidal heating, although to a lesser extent than Europa. 3 billion years ago, Ganymede's surface was undergoing massive geological changes. Its icy crust was likely thicker than Europa's but still supported by a subsurface ocean. This ocean was a result of the moon's internal heat and the presence of salts that lower the freezing point of water. Ganymede's surface was characterized by a mixture of old, heavily cratered regions and younger, grooved terrains formed by tectonic processes. These tectonic activities created ridges and troughs, evidence of the internal stresses and movements within the moon's icy shell. Additionally, the presence of a magnetic field, unique among moons, suggests a partially liquid iron or iron sulfide core, contributing to the internal heat and geological dynamism. Both Europa and Ganymede were subjected to frequent bombardment by comets and asteroids, adding to their geological complexity. These impacts not only shaped their surfaces but also potentially delivered organic compounds and other materials crucial for life. As we explore these moons today, the ancient conditions they experienced 3 billion years ago provide crucial insights into their potential habitability and the processes that have shaped them. By studying Europa's dynamic ice shell and subsurface ocean, along with Ganymede's tectonic activity and magnetic field, we gain a deeper understanding of the intricate interplay between geothermal and tidal forces in creating environments that might support life. These findings not only extend our knowledge of Jupiter's moons, but also guide us in the search for life beyond Earth, highlighting the importance of subsurface oceans and geothermal energy in the quest to find habitable worlds in our solar system and beyond. The early stages of Saturn's development were a fascinating period marked by rapid coalescence and dynamic changes. Saturn, like Jupiter, formed from the primordial solar nebula, a vast cloud of gas and dust left over from the birth of the Sun. The process began with small particles sticking together to form larger planetesimals. Over time, these planetesimals collided and merged, creating a solid core. This core then attracted surrounding gas, primarily hydrogen and helium, due to its strong gravitational pull. Saturn's core quickly amassed a considerable amount of gas, leading to the formation of its massive gaseous envelope. This period of rapid accretion resulted in the planet we recognize today, with its distinctive yellow and gold bands of clouds swirling through its outer layers. The formation of Saturn's ring system, one of its most iconic features, is equally intriguing. Scientists believe the rings likely formed around the same time as the planet, about 4-5 billion years ago. The prevailing theory suggests that the rings were created from the remnants of ancient moons or comets that were shattered by Saturn's powerful gravitational field. These fragments, composed mostly of ice and rock, gradually spread out to form the thin, flat rings we see today. Another hypothesis proposes that the rings could have formed from the primordial material that was left over after the planet's formation, which never coalesced into a moon due to Saturn's strong tidal forces. These forces would have prevented the icy particles from coming together, instead spreading them into the rings. The rings are made up of countless small particles, ranging in size from tiny grains of ice to boulders several meters across. Despite their immense width, Saturn's rings are incredibly thin, often just tens of meters thick. The particles within the rings constantly collide and interact, creating waves and structures influenced by Saturn's moons. These moons, called shepherd moons, help maintain the sharp edges of the rings and create gaps within them. These interactions are a dynamic process that continues to evolve even today. Understanding Saturn's formation and the development of its ring system provides valuable insights into the processes that shaped our solar system. The study of Saturn's rings, in particular, reveals much about the history and evolution of the planet. These natural laboratories offer a unique opportunity to observe the interactions between celestial bodies and the forces that govern their movements. As we continue to explore Saturn and its rings, we hope to uncover more about the origins of our solar system and the complex gravitational relationships that exist between planets and their satellites. This knowledge not only enriches our understanding of Saturn, but also informs our broader quest to understand the cosmos. The early atmosphere of Titan was incredibly thick, primarily composed of nitrogen with traces of methane and hydrogen. Imagine a world enveloped in a dense orange haze where sunlight barely penetrates the thick, nitrogen-rich atmosphere. Around 3 billion years ago, Titan's surface and atmospheric conditions were vastly different from what they are today, yet they already hinted at the intriguing potential for prebiotic chemistry. The presence of methane played a crucial role in Titan's early atmosphere. Methane, continually replenished by geological processes, reacted with sunlight, leading to the creation of complex organic molecules. These reactions produced a variety of hydrocarbons and nitrogenous compounds, some of which settled onto Titan's surface, forming a thick, organic-rich haze. The thick atmosphere might have also supported a methane cycle similar to Earth's water cycle, with methane existing as a liquid, gas, and possibly even methane rain. This cycle would have created lakes and rivers of liquid methane and ethane on Titan's surface, shaping its geography and contributing to the dynamic weather patterns. Beneath the thick clouds, Titan's surface was likely a cold, icy landscape with vast plains and possibly cryovolcanoes that erupted with water and ammonia instead of molten rock. These cryovolcanic processes could have brought subsurface materials to the surface, further enriching the potential for probiotic chemistry. Another key factor was the possibility of a subsurface ocean composed of water and ammonia. The ammonia acts as an antifreeze, potentially keeping the ocean in a liquid state despite the frigid temperatures. This subsurface ocean, shielded from the harsh surface conditions, might have been a cradle for the complex organic chemistry essential for the development of life. Titan's thick atmosphere also acted as a shield, protecting the surface from solar radiation and cosmic rays, allowing these probiotic conditions to persist over long periods. The presence of tholins, a type of organic compound formed by the interaction of solar ultraviolet radiation and methane, further supports the idea of probiotic activity. These tholins settled on Titan's surface, creating a complex layer of organic material that could potentially lead to the formation of more complex molecules. As we study Titan today, its early atmosphere offers a fascinating glimpse into the Moon's potential for probiotic chemistry. Understanding Titan's past helps us appreciate the intricate processes that could lead to the emergence of life and guides our search for similar probiotic conditions on other celestial bodies. By unlocking the secrets of Titan's early atmosphere, we hope to gain valuable insights into the origin of life itself and the potential for finding life beyond our own planet. The early stages of Uranus formation present an intriguing tale of unique characteristics and conditions. Unlike the other gas giants, Uranus is tilted on its side with an axial tilt of about 98 degrees. This extreme tilt likely resulted from a massive collision with an Earth-sized object early in the planet's history. Such an impact would have dramatically altered Uranus' rotation and significantly influenced its climate and atmospheric dynamics. Imagine a planet forming from the primordial solar nebula as small icy and rocky bodies coalesced to form a core. This core then attracted surrounding hydrogen, helium, and other gases, enveloping Uranus in a thick, gaseous atmosphere. Early Uranus would have had a dynamic climate, characterized by intense storms and possibly even a more substantial heat flux from its interior. The impact that caused Uranus' tilt would have led to drastic changes in its climate. As a result, the planet experiences extreme seasonal variations, with each pole getting around 42 years of continuous sunlight followed by 42 years of darkness. Picture an atmosphere rich with hydrogen, helium, and methane, the latter giving Uranus its characteristic blue-green color. The methane absorbs red light and reflects blue and green, creating its distinctive hue. The past climate of Uranus might have been more active than it is today. The extreme axial tilt would result in complex weather patterns, with the sun heating different regions of the planet for prolonged periods. This heating could have driven powerful winds and storms, leading to a dynamic and ever-changing atmosphere. The internal heat of Uranus would also play a role in shaping its weather. Despite being a gas giant, Uranus emits very little heat compared to other planets like Jupiter and Saturn, and it's one of the coldest planets in our solar system. However, this doesn't mean it was always so quiet. There might have been periods of more significant internal activity, contributing to a more turbulent atmosphere in its early stages. Understanding the formative years of Uranus and the unique conditions created by its extreme axial tilt helps us appreciate the diversity of planetary climates within our solar system. This knowledge not only enhances our understanding of Uranus itself, but also informs our broader search for exoplanets with unusual orientations and climates. By studying Uranus' early stages, we gain valuable insights into how giant impacts can shape planetary characteristics and the potential for diverse and dynamic atmospheres beyond our solar system. The formation of Neptune is a captivating story of dynamic development and atmospheric evolution. Imagine a young solar system filled with gas and dust when Neptune began its journey as a small, icy core. This core, composed of rock, metal, and ices, started to form in the outer reaches of the solar nebula far from the Sun. Over time, this core accumulated surrounding gases, primarily hydrogen and helium, through a process known as runaway accretion. Neptune's early development was marked by its rapid growth and the acquisition of a substantial atmosphere. This gaseous envelope, enriched with methane, gives Neptune its striking blue color. The methane in Neptune's atmosphere absorbs red light and reflects blue, creating the vivid blue hue that distinguishes the planet. Neptune's atmosphere is incredibly dynamic, and it was no less colorful and active in its early days. Picture a world with powerful winds and storms driven by the planet's internal heat. Neptune's internal heat, likely generated by the gravitational energy released during its formation, contributes to its active climate. This internal heat flux, combined with the planet's rapid rotation, creates the fastest winds in the solar system, reaching speeds of up to 500 miles per hour. Around 3 billion years ago, Neptune's atmosphere was both complex and turbulent. Massive storms larger than Earth itself roamed across the planet's surface. These storms, fueled by the planet's internal heat and dynamic weather patterns, created a constantly changing atmosphere. Neptune's Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, is an example of the intense atmospheric activity that likely characterized the planet's early years. The presence of bright, wispy clouds made of methane ice crystals added to the dynamic nature of Neptune's atmosphere. These clouds formed at high altitudes, driven by the planet's powerful winds and heat. As we delve into Neptune's formation, we uncover a world of rapid development and ever-changing weather patterns, shaped by the interplay of internal heat and atmospheric dynamics. Understanding Neptune's early development and dynamic atmosphere helps us appreciate the complexity of planetary formation in the outer solar system. By studying Neptune, we gain valuable insights into the processes that govern the formation of ice giants and the unique characteristics that distinguish them from other types of planets. This knowledge not only enriches our understanding of Neptune, but also informs our broader search for exoplanets with similar characteristics, guiding us in the quest to find other dynamic and intriguing worlds beyond our solar system. The state of the Kuiper Belt 3 billion years ago was a fascinating period of formation and evolution. Imagine a vast, distant region of our solar system, extending beyond the orbit of Neptune, filled with icy bodies and remnants from the solar nebula. This area, known as the Kuiper Belt, was teeming with countless objects that would later become some of the most intriguing celestial bodies we study today. The Kuiper Belt was in a state of dynamic change, with objects colliding, coalescing, and evolving over time. One of the most well-known objects in this region is Pluto. Around 3 billion years ago, Pluto was in the final stages of its formation. It started as a collection of icy and rocky materials drawn together by gravity. These materials came from the Primordial solar nebula, the same cloud that gave birth to the Sun and the rest of the solar system. As these particles collided and stuck together, they gradually built up into larger planetesimals. Over time, these planetesimals merged to form Pluto, giving it the composition we observe today, which includes a mixture of rock, water ice, and various frozen gases such as nitrogen, methane, and carbon monoxide. The early environment of the Kuiper Belt was chaotic. Frequent collisions between objects caused fragmentation and redistribution of materials, leading to a constantly shifting landscape. These collisions also created a range of sizes among Kuiper Belt objects, from small chunks of ice to dwarf planets like Pluto and Eris. In this early period, the gravitational influences of the gas giants played a significant role in shaping the Kuiper Belt. The migration of Neptune, in particular, had a profound impact. As Neptune moved outward, it scattered many objects into the Kuiper Belt and caused others to become more dynamically stable in their distant orbits. This migration likely led to the current distribution of Kuiper Belt objects that we observe today. Understanding the Kuiper Belt 3 billion years ago provides us with valuable insights into the formation and evolution of our solar system. The study of Kuiper Belt objects like Pluto helps us piece together the history of the outer solar system and the processes that led to the creation of these distant icy worlds. These objects are considered time capsules, preserving the conditions and materials from the early solar system. By analyzing their composition and structure, we gain a better understanding of the primordial environment and the factors that influenced planetary formation. The Kuiper Belt's dynamic history and the intricate dance of its objects continue to captivate scientists and enthusiasts alike as we seek to unravel the mysteries of this distant frontier. As we continue to explore the Kuiper Belt, both through telescopes and space missions, we hope to uncover more secrets about the early solar system and the forces that shaped it. This knowledge not only enriches our understanding of our own cosmic neighborhood, but also informs our search for similar regions around other stars, guiding us in the quest to discover more about the universe and the potential for life beyond our solar system. The role and conditions of comets and asteroids in the early solar system were pivotal in shaping the dynamic environment we know today. Picture a time when the solar system was a bustling region of celestial activity, with countless comets and asteroids zipping through space. These small, rocky, and icy bodies were the building blocks of planets, holding clues to the early solar system's composition and the processes that led to planetary formation. Comets, often described as dirty snowballs, were composed of ice, dust, and organic compounds. As they traveled through the solar system, their icy nuclei interacted with the sun's heat, creating spectacular tails of gas and dust. Around 3 billion years ago, these comets played a crucial role in delivering water and organic molecules to the inner planets, including Earth. Imagine a young Earth bombarded by comets, each impact enriching the planet's surface with essential ingredients for life. This period of heavy bombardment, known as the Late Heavy Bombardment, likely contributed to the formation of Earth's oceans and the introduction of complex organic molecules that would become the building blocks of life. Asteroids, on the other hand, were rocky remnants from the early solar system's formation. Found primarily in the asteroid belt between Mars and Jupiter, these bodies varied in size from small rocks to large planetoids. The gravitational influence of Jupiter played a significant role in preventing these rocky bodies from coalescing into another planet, maintaining the asteroid belt as a distinct region. These asteroids were involved in frequent collisions, breaking apart and reforming, continuously reshaping the landscape of the early solar system. Some asteroids, known as planetesimals, were large enough to undergo differentiation, developing a crust, mantle, and core similar to planets. Both comets and asteroids served as cosmic delivery vehicles, transporting water, organic compounds, and other essential elements throughout the solar system. Their impacts on young planets not only contributed to the chemical richness necessary for life, but also impacted geological and atmospheric conditions. For example, asteroid impacts would have caused significant heat and energy release, influencing volcanic activity and possibly contributing to the formation of early atmospheres. As we study these ancient celestial bodies today, missions like the Rosetta spacecraft to Comet 67P and the OSIRIS-REx mission to asteroid Bennu provide valuable insights into their compositions and the roles they played in the early solar system. By analyzing the materials found on comets and asteroids, scientists can reconstruct the conditions of the primordial solar nebula and understand the processes that led to the formation of planets and the emergence of life. The dynamic interactions between comets, asteroids, and planets highlight the complex and interconnected nature of our solar system's history. Understanding these processes helps us appreciate the delicate balance and the multitude of factors that have contributed to the development of habitable environments. As we continue to explore these ancient remnants, we unlock vital clues about the early solar system, guiding our search for life and understanding of planetary evolution beyond our own cosmic neighborhood. Interplanetary environment described the overall environment of the solar system, including solar wind and space weather conditions 3 billion years ago. The interplanetary environment of our solar system 3 billion years ago was a dynamic and bustling realm shaped by the intense activity of the young sun. During this period, the sun was more energetic and active than it is today, emitting powerful solar winds and frequent solar flares. These solar winds, streams of charged particles like protons and electrons, flowed outward from the sun at high speeds, permeating the entire solar system. Solar wind plays a crucial role in shaping planetary atmospheres and magnetospheres. Picture a time when the solar wind was more intense, interacting with the magnetic fields of planets like Earth, Jupiter, and Saturn. These interactions generated spectacular auroras and influenced the retention and loss of atmospheric particles. The young sun's vigorous activity also meant that space weather was more extreme. Solar flares and coronal mass ejections were more frequent, sending shock waves of energetic particles traveling through space. When these particles collided with planetary magnetospheres, they could cause geomagnetic storms, impacting everything from atmospheric chemistry to surface conditions. These space weather phenomena had significant effects on the solar system's environment. For instance, the ionization of atmospheric particles by solar radiation and energetic particles could have influenced the development of early atmospheres and possibly even the conditions necessary for life. The solar system's heliosphere, the bubble-like region of space dominated by the solar wind, was also more dynamic and expansive. This heliosphere acted as a protective shield, deflecting cosmic rays and interstellar particles. However, because the solar wind was stronger, the boundary of the heliosphere fluctuated more dramatically, sometimes exposing the inner planets to higher levels of cosmic radiation. This fluctuation had implications for the development of planetary atmospheres and surface conditions, as increased radiation could affect the stability and chemistry of early atmospheres. Beyond the influence of the sun, the interplanetary environment was shaped by the gravitational interactions between planets. These interactions influenced the movement of asteroids and comets, leading to frequent collisions and scatterings. The migration of giant planets like Jupiter and Saturn also played a significant role in shaping the distribution of smaller bodies and the overall architecture of the solar system. The early solar system was a place of constant change, with gravitational forces, solar radiation, and particle fluxes interacting in a complex dance. These factors collectively shaped the environments of planets and moons, setting the stage for the development of atmospheres, surfaces, and potential habitability. By understanding the interplanetary environment of 3 billion years ago, we gain insights into the foundational processes that have influenced the evolution of the solar system, guiding our exploration and search for life in the universe. Comparative analysis compare and contrast the conditions of all these bodies to highlight similarities and differences. The first significant similarity among Earth, Mars, and Venus 3 billion years ago is the presence of water in some form. Earth had its primordial oceans teeming with early microbial life. Mars had vast river networks and possibly lakes sustained by a thicker atmosphere, and Venus might have had liquid water on its surface before a runaway greenhouse effect transformed it. However, the conditions for retaining this water differed dramatically. Earth's stable, moderate greenhouse effect, along with its magnetic field, helped retain its atmosphere and water. In contrast, Mars' atmosphere gradually thinned due to solar wind stripping, causing its water to evaporate or freeze. Venus, on the other hand, experienced extreme volcanic activity that released massive amounts of carbon dioxide, initiating a runaway greenhouse effect that boiled away its oceans. While Earth was developing a rich, dynamic biodiversity within its early oceans, Mars and Venus were veering towards vastly different fates, one becoming arid and cold, the other exceedingly hot and inhospitable. Exploring the outer solar system, we see a different story. Jupiter and Saturn, as gas giants, never had solid surfaces with water but played crucial roles in the solar system's architecture. They influenced the movement and formation of other bodies, including the delivery of water to inner planets via comets. Jupiter's strong magnetic field and immense gravity helped shape the asteroid belt, while Saturn's early development included the formation of its iconic rings, which may have resulted from shattered moons or comets. Their powerful gravitational fields acted as cosmic vacuum cleaners, drawing in or deflecting many would-be impactors, thus contributing to the relative stability of the inner solar system. The moons of Jupiter, particularly Europa and Ganymede, offer another fascinating comparison. Both moons likely harbored subsurface oceans beneath their icy crusts due to tidal heating from Jupiter's gravitational pull. Europa's thinner ice shell and more dynamic surface suggest more active geological processes, potentially fostering conditions similar to Earth's hydrothermal vents where life might arise. Ganymede's thicker ice and evidence of tectonic activity, along with its magnetic field, point to a complex internal structure that could also support a hidden ocean. These moons, though vastly different from Earth in terms of surface conditions, might share similarities in their potential for harboring life in subsurface environments. Turning to the ice giants Uranus and Neptune, we notice unique characteristics influenced by their compositions and axial tilts. Uranus, knocked onto its side by a colossal impact, experiences extreme seasonal variations unlike any other planet, with each pole facing the sun for decades. Neptune, with its vivid blue color from atmospheric methane, boasts the fastest winds in the solar system. Both planets have dynamic atmospheres and magnetic fields, but differ in their internal heat. Outputs Neptune emits more heat, whereas Uranus appears comparatively colder. These distinctions underscore the diversity of planet-forming processes in the outer reaches of the solar system. Lastly, the icy bodies in the Kuiper belt, like Pluto, and the comets and asteroids further highlight the diversity of solar system conditions. Pluto, with its nitrogen ice plains and potential subsurface ocean, reflects a miniature version of the processes seen on larger planets. Comets and asteroids, as ancient remnants, provide vital clues about the early solar system's composition and the delivery of essential elements to forming planets. While these bodies range widely in size and composition, they collectively contributed to the chemical richness necessary for life. In summary, the comparative analysis of these solar system bodies reveals both striking similarities and profound differences shaped by their unique formations and evolutions. Understanding these ancient conditions not only deepens our knowledge of planetary science, but also guides our search for life and habitable environments beyond Earth. The diversity of environments, from the watery past of Mars and Venus to the dynamic icy moons of Jupiter, underscores the myriad paths planetary development can take, informing our quest to find other worlds like our own. In summary, delving into the planetary conditions of 3 billion years ago reveals a tapestry of dynamic environments, each offering unique insights into the processes that shaped our solar system. Understanding Earth's early atmosphere and volcanic activity helps us appreciate the extreme conditions where life first took root. Mars, with its ancient rivers and lakes, suggests that the red planet might have once harbored life, urging us to continue exploring its past and present for signs of microbial existence. Venus' transformation from a potentially habitable world to a scorching desert underscores the delicate balance required for maintaining a stable climate. The geological and gravitational interactions between Earth and the Moon reveal a complex dance that influenced the development of both bodies, highlighting the interconnectedness of celestial mechanics. Mercury's heavy volcanic activity and frequent impacts offer a window into the turbulent early solar system, while Jupiter's formation and gravitational influence were crucial in shaping the orbits and stability of the inner planets. The icy moons of Jupiter, Europa, and Ganymede, with their subsurface oceans, expand our understanding of potential habitats for life beyond Earth. Saturn's majestic ring system and its formation provide clues about the primordial solar nebula and the dynamic processes at play. Titan's thick methane-rich atmosphere hints at probiotic chemistry, suggesting that conditions suitable for life's building blocks might exist elsewhere. Uranus' extreme axial tilt and Neptune's vibrant atmosphere remind us of the diversity of planetary climates and the impacts of colossal collisions. The Kuiper Belt and its icy residents like Pluto offer a glimpse into the early stages of planetary formation and the role of these distant objects in delivering essential compounds across the solar system. Comets and asteroids, as ancient remnants, continue to be key in understanding the early solar system's composition and the delivery of water and organic molecules to Earth. Studying these ancient conditions is not just about looking back, it's about guiding our future research and exploration. By uncovering the secrets of planetary pasts, we refine our techniques in the search for life beyond our planet, helping us identify habitable environments on exoplanets. The lessons learned from our own solar system's history inform our strategies in exploring new worlds, fostering a deeper understanding of how life might arise and endure in the cosmos. As we continue this journey of discovery, the ancient tales of our neighboring worlds will light the way, revealing the delicate threads that weave the fabric of our universe and our place within it. So, if you enjoyed this deep dive into the past, make sure to like this video, subscribe to the channel, and hit the notification bell to stay updated with our latest explorations into the wonders of the universe.